Hello, everybody. How's it going? So, today I'm going to be talking about cryptography. And I kind of treat cryptography as this kind of hidden layer or this layer that's has the goal of like hiding information. And this is part of a construction that, I have this kind of five-layer thing here that I call information physics. It's just, it's going to help me refer to these sorts of this sort of background that I would expect like people to understand, like how information can be stored as a physical state, in like transistors or in some kind of even more abstract like Turing machine, as well as how information gets propagated in the form of like radar or like as a waveform and packeted by TCP/IP routing, and then having some kind of shared distributed compute across like a global network, or causal networks, really, and making sure that there's consensus, all of those things. And then the hidden part is really what cryptography is all about. And then contested is more like kind of cyber warfare type stuff. So, um, yeah, so the whole idea is about cryptography is that, you want to hide information from adversaries who may see it, or they might be able to see some channel or some ciphertext or even parts of a system. So security itself is not invisibility, and it's never going to be invisible because it's just physics. If you're doing something on a network, it's and really the whole point of cryptography is to hide things. So security is just about making that extraction of information computationally infeasible. So you don't want to remove. Oh God, sorry. You basically don't want to remove information from the world, I would say, like because that would exchange. You would have to exchange some cost, like from like of extracting it from that. So that's how I'm gonna frame the idea of cryptography in this information physics idea. Okay. Now, information is not really just going to be stored or transmitted or shared. It's cryptography is going to replace the physical secrecy with mathematical hardness. That's the whole idea. So, if you have a hard problem, make a really, really hard mathematical problem and ensure that it gives you a very expensive extraction. So, you want to say like really, I mean, you security is conditional as well. That's a very important point because what it does is it transforms access into inference, right? And an attacker cannot, it does not need permission to try, attacking. What they do is what they need is resources. And so cryptography is another way. It's kind of a resource theory of hiding information itself. So that's another kind of way to frame the problem. Because algorithms are public. I mean, even in cryptography, like somebody could just come up with a random algorithm that nobody's ever thought of before, and that just if you don't have the right frame to particularly attack that problem, then you're not going to be able to crack it, right? Or people are not going to be able to actually read what's in there. So cryptography is not unbreakable. It's just conditional on some assumptions. So again, that idea of conditionality. Some parameters, some implementation, some threat model, whatever it is. So what you have to do is think about the absolute, the conditional, and the physical security. So information. There's three different regimes of, and of course this is really just the schematic, but there's three different regimes that you're really working with in cryptography. And you'll start off with just this information theoretic security and computational theoretic security, and then provable security. That break some scheme and then solve a hard problem. Now, in general, um, the implementation shouldn't leak as well. So there's also kind of this physical boundary as well to the energy that you're expending to mine some particular algebraic lattice that's abstractly has some information with some I don't know, you could calculate the energy that it takes to mine a Voronoi tessellated or hyper volume of like some lattice or whatever, and then like estimate the computational energy that's needed to mine it or to crack it. But essentially, how you want to think about this is if you have adversary A breaks some scheme with advantage E epsilon, then adversary B solves a hard problem with advantage epsilon over in polynomial lambda. Okay, so that's kind of a nice reduction. So just because you have, if you're able to prove, if you're able to break something, you get reductions, and you're able to quotient out, the fact that the adversary broke it already. So, devices live in physics, and so that's very important as well. So that's essential to understanding things. Now, there's one thing called the one-time pad, and the one-time pad is very interesting because it's unconditional and it's information theoretic, and it actually has very expensive key logistics. But basically, the ciphertext reveals absolutely nothing about the plain text, using Bayes' theorem. And this requires a perfect key distribution, and the key is as long as the message. So, like, if you were to perfectly obscure this, we have already basically solved perfect secrecy with the thanks to Shannon. Okay. But that's unscalable. So what we need to do, and of course we can try to prove this, there is exactly, one key such that if we were to take some uniform k, every m gives us equally likely, from Bayes' theorem and such. So hence, the Shannon entropy given, this is the definition of Shannon entropy here. Given some c, m given c, if you take the difference between both of them, you get 0. So there's no leakage there from an information theoretic standpoint, from ciphertext to plain text. All right. And you can look at like some bitwise examples as well. You could just take with a XOR gate or a XOR gate, XOR, however you want to pronounce that. But it essentially allows you to have the registers put the bits, on the registers and allow them to do the operation that gives us the ciphertext to plain text, and it's perfect. Okay, there's no loss of Shannon entropy in that case, no information leakage, so it's perfectly encrypted, perfectly hidden. So provable security. If factoring is hard, then RSA is secure in a precise game. So how we can think about this is basically cryptography is not just one kind of security. You can think of it as like having a stack of different security regimes. So if we were to take a security game here, let's say INDCPA, this is a adversary that distinguishes encryptions of two messages. We can assume an adversary wins with advantage this, construct this, as we were talking about with the advantage by physical reduction. We can break the scheme, transfer hardness, and get that security is conditional on the assumption. So that would be a nice provable security. Now we can actually utilize this for understanding classical primitives. So if we look at symmetric cryptography, you can think about this as substitution and also some diffusion over a finite field for round operations. So this would be 4 round operations. I think SHA-256 does like, I don't know how many round operations on its it's probably like 64 or something like that. That's a guess. Or 32. 64 or 32. They always do it in powers of 2. But it's always powers of 2. Just remember that. computers and stuff. So, um, but yeah, so you have the AES here. It's just a substitution, right? So you take a nonlinear S box, confusion. So it's got like some randomness, and then you have your sort with round key, linear diffusion over columns, and then the confusion diffusion resistance to differential linear cryptanalysis. You'll have this nice particular uh, construction of some nice This is symmetric cryptography. So it's symmetric in the sense that like you're getting these this kind of transparent reversibility within the action of doing these round operations, and there's just only four of them. Okay, yeah, and then if you were to take the SHA-256 algorithm, this one's not symmetric because as you continue to do, you have words, right? And these words are represented by bits, and then the bits are getting scrambled, or the words themselves are getting scrambled with different types of operations, and they split into blocks, with some compression function, and then yeah, so you'll get a nice collision resistance here without any practical breaks, but you'll get reduced round attacks that can exist. That's why we mine. That's why we use SHA-256 for mining Bitcoin, because SHA-256 encrypts, or it's a good hiding mechanism for the tuple, I guess, that is Bitcoin, of sender and transaction size and volume blocks, for blockchain technology. So yeah, and then of course, as you're mining these SHA-256 types of compression, these compressed like blocks, if you will, there's like a Poisson distribution, or like it obeys Poisson statistics on how they reward Bitcoin. So, anyways, RSA, you can just think about this as, it's pretty much just prime number arithmetic. There's nothing really super special about RSA besides the fact that it's a public key. So, yeah, I mean, it is hard because of the prime factorization. Prime factorizations are pretty, or integer factorization. Um, with primes themselves, you have like certain computational assumptions, and then after you mod out the integers for those specific set of primes, you would get some key, or it would generate some public key. Now the decryption works because it's just arithmetic hiding. Multiplication is pretty easy, but if you reverse it, it's believed hard for semi-primes. So we believe that it should be, the multiplication or reversing it should be hard for semi-primes. That's essentially all that you really need to know about this. Let's look at an example here. I mean, you can look through the proof or the claim itself, but you just take 3 and 11, right, which gives us n is 33, and then take our 5 function to be 20, and take e and d to be 3 and 7. Since this, we can mod out 20, so we get this. Yeah. So then when you encrypt, m is equal to 5 and c is 5 to the third, and mod out 33. 33 mod, oh, sorry, 125 mod 33 would give us 26, and then you decrypt. Okay, yeah. And then what that did is we were able to decrypt 26 to 37, or 26 to 37 mod 33. That gives us 5. Ooh, okay. So that's how you would do an RSA type. I mean, this is just a toy example for the actual function that's constructed here, for p minus 1, q minus 1. Okay. Now, we can also look at ECC. So, okay. First of all, before we look at ECC, essentially the main goal, if you didn't follow the RSA encryption, just take that we have some easy direction for some public encryption, but if you assume that asymmetry of the semi-primes, then you get hard a hard direction to recover D. All right. So this asymmetry in the encryption is part of what fuels a lot of modern cryptography schemes. Now we can look at elliptic curve cryptography. Now this is just the discrete logarithm problem essentially. Um, so that's if you were to sum up elliptic curve cryptography, that's what it is. And you can move on to finite elliptic curves, because it's essentially it's geometric hiding. So you have an inverse problem that's recovering some secret scalar k, right? And the public operation is a scalar multiplication. So the elliptic curve discrete logarithm this is a very powerful because the geometry will give you smaller keys for comparable classical security levels. So the one-time pad here is kind of a nice clean mathematical ideal of this from the one-time pad, which was the very first scheme that we looked at over. But if the key is uniform or it's secret and used once, as long as the message, then we would have that P of M, right? Or that we would have that P, the expectation, right? I'm sorry, the probability of getting P, the probability of getting M given C is equal to just the probability of M itself. So the ciphertext will give you nothing. But, so elliptic curve cryptography is going to basically hide by this finite kind of geometric motion, and versus the one pad that is hiding the entropy. It's just hidden by entropy itself, by informational entropy. So RSA, though, I don't want to overstate anything. RSA is not equivalent to factoring in every formal sense. So if you say RSA style security is tied to some under assumed, I guess, hardness of factoring under precise scheme assumptions, that's kind of like more accurate, right? Whereas if you were to say elliptic curve cryptography, it's not quantum safe, right? That's another thing. Whenever you say something is quantum safe, it's just not safe against a sufficiently large, fault-tolerant quantum computer running Shor's algorithm. So that's a very specific like instantiation of the goals of cryptography, right? What are the goals behind it, and what particular information should be obscured or hidden, from the rest of the world, right? That's on the internet. So yeah. Next, we'll talk about quantum threat and post-quantum hiding. So this was requested in the Discord. Was Shor's algorithm. I'm not gonna go super into number theory. I think that was another request. Also, shout out to McSnuffle Wumpington. Um, if you know, you know. Okay. I hope McSnuffle Wumpington's. I hope that stream of words in a bit. I hope that becomes like the first basis of cryptography, like McSnuffle Wumpington. Just like that is the shortest vector decomposition. Like that is the eigenvalue. Like in the lattice is McSnuffle Wumpington. Okay. Anyways, that was not meant to be cryptic at all. Okay, this is not a meta cryptography type of lecture. Okay, don't read too much into this. Okay. Anyways, Shor's algorithm. So basically, you just want to find the period. It's period finding that breaks factoring with a discrete logarithm. And you use something called a quantum Fourier transform. It just has to do with taking a regular a regular Fourier transform and Schrödingerizing it onto a quantum computing array. Basically, I mean that's all it is, and it just reduces the factoring to a discrete logarithm and breaking RSA and ECC and polynomial time, because that's really all about what's happening is the polynomial time, you know, versus like quadratic um, or more exponential or even factorial time. Like we want to um, utilize the extreme state space of the quantum computers that allow us to actually do this problem. And so, yeah, I mean, you can think the quantum thread is not really, it's not that quantum computer tries all keys at once in some naive way, like the internet will tell you. The real issue is the structure. So what happens is the RSA and the ECC contain hidden periodic structure, because it's just like the universe, like everything's just waves and shit. So yeah, so you'll have like Shor's algorithm that gives us quantum Fourier methods and extract that period efficiently. Once that period is known, factoring and discrete logarithms can become very tractable, which is nice. And that breaks the old public key world. So post quantum cryptography will look for problems that there's just no efficient quantum algorithm that is known. So that's why they call it post quantum cryptography, right? Lattices. Lattices are a form of post quantum cryptography because they're one of the most important candidates for this. Um, it's not completely set in stone whether they're going to be post quantum, um, but it's worth researching because a lattice is an infinite grid generated by basis vectors, and in 2 dimensions it looks pretty simple, but in hundreds or thousands of dimensions the geometry becomes computationally hostile. It takes a lot of energy to probe such an algebraic lattice. So the shortest vector problem here is going to ask for an unusually short non-zero lattice vector, and the closest vector problem asks for the lattice point nearest to the target itself. And so that just becomes a very difficult type of problem setup, as you can see. And so that's essentially how you would, just the closest vector problem, shortest vector problem, are two cryptography things. Also, the LLL basis reduction or LWE basis reduction, there's other things. They hide secrets inside of noisy linear equations. So the noise becomes like a shield. So you're like shielding it with a bunch of, let's see, this is the learning with errors. But LLL basis reduction is just essentially this way of decomposing, with Gram-Schmidt, read Apostle Volume 2, or read She Loves Linear Algebra on the generalized Gram-Schmidt process in Euclidean space. But that's essentially everything. It doesn't break with modern lattice schemes at recommended dimensions, so it's nice. It's nice for cryptanalysis of weak parameters. But LWE will, if you take the linear equations and you add noise to them, the noise shields this from, prevents the exact linear algebra from recovering the secret itself. And so kind of back to LLL, it's important because it's going to show that the lattices are not completely opaque, right? You can find somewhat of a short vector in polynomial time, but somewhat short, again, is not the same as the shortest vector. So the distinction between is the gap cryptography that lives inside, and the lattice cryptography is about choosing the parameters where the known reductions are too weak to recover that secret efficiently. Okay. Now, there's also lattice signatures, so you can think about Bliss and dilithium. I've actually played around with making some really heavy chains with dilithium. So that's a fun thing if you wanted to like actually create a cryptocurrency that uses post quantum overkill lattice cryptography. Then go ahead and do that. It might be fun. But yeah, so you don't really lattice-based schemes. They're just designed around problems where there's no efficient quantum or classical attacks known at these chosen parameters that we know of. Okay. Zero knowledge and fundamental limits. Okay. Um, a prover. So here's the idea of a zero knowledge proof. They exist. A prover exists W without revealing W, or prove there exists some W without revealing W. Okay, so that's how you think about it, with W as a witness. So you want to prove that there was a true witness. It's kind of meta, but the security is going to live inside some assumptions and models. The device may still leak as well, timing, power. There might be electromagnetic traces or cache behavior that's kind of weird. But overall, this is what the zero knowledge proof is trying to do. So it's basically it's one of the most elegant ideas in cryptography, because the prover here, this prover convinces the verifier that a statement is true without revealing the witness. And then the witness itself is the hidden object, which is very cool and exciting, because the proof itself is the public object. And you could have some example, some example structure here. But the verifier will learn that some valid witness exists, and then the verifier should not learn from the witness itself. This is the precise version of just show me that you know without telling me what you know. That's a nice way to think about it. Okay. Now, ZK snarks, zero knowledge snarks. They add succinctness because the proof can be much smaller than the computation it verifies, and verification can be very fast. But the succinctness usually comes with some assumptions as well, like polynomial commitments, pairings, random oracle models, knowledge assumptions. So there's a bunch of different ideas as well that get translated between the ZK snarks blockchain without exposing any private inputs. Now we can look at impossibilities and separations. The Impagaliazio, Rudrich. I didn't practice saying that. I'll just say IR. Infrared. IR infrared. No black box construction of public key encryption from one-way functions alone. Whereas if you have a security in the random oracle model that's needed, that doesn't imply any standard model security. Composition failures. So again, the proofs bound the models, but they don't guarantee the end-to-end security in deployment itself. So that's kind of the next, problem that we would have to think about. But a proof always needs a formal model, and a real machine is more than a formal model. So you can have timings with secret dependent branches. Power draw can reveal arithmetic. Electromagnetic radiation from your computer can leak computation itself. Cache behavior. Fault injection. You can push a device to the outside and assume computation. You can even have protocol composition that breaks guarantees. That just guarantees that even if there is a piece, it can just break any sense of feeling that you have that's guaranteed that each piece is secure alone. So that's very important. So, the proof will always be correct while the device betrays you. That's another way to think about this for proof-based models. So, physical devices leak. We have, power, electromagnetism, timing, cache memory, fault injection. So just as I was saying, you can have a bunch of side channel attacks as well with these types of zero knowledge proof systems. All right, synthesis. We will synthesize everything today. So, essentially, you think about cryptography gives you mathematical hiding, and it's not some isolated topic because it sits inside of the full physical life cycle of information. So first, you can think about information itself is stored in matter, and then it's going to propagate itself as a waveform, as I talked about earlier. And then it gets shared across these distributed causal networks that we call the internet. And then it's hidden from mathematical hardness. And then, of course, you know, by intelligent adversaries, they're always going to be contesting what is true, what is false, etc., and basically writing history. So, encryption does not remove thermodynamic cost. It also doesn't remove bandwidth cost. It also doesn't remove latency or consensus cost. It just adds this hidden layer is just a new expense. It's the computational extraction of the information itself because we had to hide it. So that's the point of really this cryptographic shield, if you will, that we have talked about. So again, we talked about one-time pads, so just secrecy from entropy itself, RSA and ECC, secrecy from arithmetic or geometric hardness. Lattices give us secrecy from high-dimensional noisy geometry. Zero-knowledge proof just gives us the truth without witness transfer. And side channels like physics, leaking through the abstraction itself. That's or in the Internet of Things, if you will. That was something that I learned from my fellow jet space Discordians. But yeah, so cryptography, you can think about this as just the science of arranging information such that the truth remains usable, but extraction is just very expensive. Okay, so yeah, that's pretty much all I have for you guys today. Thanks for watching, and I'll try to be more active. And yeah, peace out.